computer. Okay, now let me ask you one thing. Suppose that I have A, B, but now this is a plus, it's not a minus. So this is equivalent to what? You know the result above. So without doing computations, what is the equivalent of this interconnection?
A divided by 1 minus AB.
A divided by 1 minus AB. Why?
So we only change the sign.
So we put a minus here if I want, but if I put a minus here, I should put a minus here. So I put a minus here and I change B to minus B. So that minus B times minus 1 becomes B plus B. Okay? So this king is equivalent. When I put a minus here and minus B, then apply the result above. Now, suppose that I have another thing, which is B with a minus. This is what?
One divided by 1 plus B.
1 divided by 1 plus B. B. That's right. Okay. What about if I have something which is A and then init feedback plus minus? This is very easy. So what is the equivalent?
A divided by 1 plus A.
Okay. Now, the big trick is to memorize this stuff here. Okay. And this is what? This is the direct gain. I call it the direct gain between the error and the output, divided by 1 and plus the loop gain. This is the loop gain. So you go around this loop, you multiply all the gains, and all the gains are A and B. So it's 1 plus A and B.
Interesting.
Okay? That's the way to memorize things. Okay, now let's apply what this trick to there, plus the fact that the system is linear, so we have superposition. So T is equal to, let me use the same color. Let me be consistent with the color. So T, good luck. T is equal to the transfer function times the reference plus the transfer function times D plus the transfer function times N. Okay, so what are these transfer functions? So, and I consider the effect of R on T is assuming that D and N are zero. So when I'm studying the effect of R on T for a linear system, I assume that D and N are zero. So for T, for the influence of R, what is, you remember, it's the direct gain divided by the loop gain. So for R, what is the loop? What is the direct gain? What is that red part?
GK.
Okay, kg. It's the same, but kg. And the loop gain is the product of all the elements in the loop. So
1 plus
1 plus
kg or gk or whatever you want.
kg.
Now, for D, this is tricky. This is tricky. So what is the direct gain now? From D to T?
1.
1. Because you just go from here to here. And the loop gain? You go around?
1 plus kg.
1 plus kg. And remember that you have this minus here that you can transport because R is 0. You can transport to there. Okay, so you can rewrite this as a feedback in which loop in which A is just 1 and B is kg. Now for N, what is the direct? Now you are from here to T. So what is the loop gain? The direct gain?
It's minus
Minus
kg or gk.
kg or kg. If it is a scalar, it is immaterial. It's just a matter of state of taste.
Divided by 1 plus
1 plus
kg.
kg. Now let's. The game is that T tracks R, but is not affected by D or N. So kg should be what? Here. For T to be close to R.
big.
Kg big. Here.
Also big.
Big because 1 divided by a big thing is a small thing, big. And here?
Small.
Small, yeah.
Small. Okay? So we have a problem. You have an idea how can we solve this problem? Well, the problem is solved in this way. Up to now, for us, we were just considering this as gains, as numbers. But you know, for instance, that G is not just a number. It's a dynamic system. You apply something to it. Okay, so there is, you can make K depend on the frequency. You can K depend on the frequency. Okay, imagine that you decompose your system in frequency domain. Okay, and you change K according to the frequency. So think of the harmonics of the signal that K is receiving, and you decompose. This seems very complicated, but actually it's not complicated. I will show you how to do it in a very simple way. So let's clean up the trick. You are familiar now with the basic algebra, or you want to make some question?
No.
Because now we are going to something which is more difficult.
Mm-hmm.
Okay.
Let's go.
Okay, so we enter what we call the frequency domain. So we have frequency. And I have K, okay? And I have K. Now, I will use, this is a log scale, okay? This is a logarithmic scale, log scale. Where is for K, for kg? Okay? Where is kg equal to 0? Here? Assuming that this is a log scale, kg equal to 0, what is the position on this vertical axis?
1.
1. Yeah.
1. So you write here something which is 1. So this is 0, and this is 1, and log of kg equal to, or kg equal to 0 corresponds in a log scale to position 1. What is the
No.
logarithm of 1?
Yeah, sorry. We are computing the logarithm.
Logarithm of
kg.
1 is what?
It's 0.
0, okay. So, and the logarithm of 0 is what?
It isn't defined, right?
It's not.
Oh, it is defined, but it's
It goes to minus infinity.
minus infinity. Okay, it's minus infinity. Okay. So kg equals 0 is not here. So you only see very small values. Now, let's put these barriers such that we have such barriers such that we satisfy this constraint. So let's clean up this thing which is not useful here. And now I say specification such that you track the reference. So kg must be big, must be above something. So I put a barrier here. It should be at least above. This is okay. The higher kg, the smallest the error. Now, to track, to reject a disturbance. Reject a disturbance is this. Suppose that you have a staircase, a moving staircase. Okay, you go to Chiado in the underground, and then you have to climb in the staircase. Okay, and the staircase is moving with a constant velocity. And you step on the staircase, you are a disturbance. Okay, and you want to keep the velocity. As simple as that. So you are a disturbance. Something that it's a load to the system. In a thermal system, you open something that enters or that makes temperature to be lost, say. Now, if you want to reject the disturbance, kg should also be big. So let's assume it's the same barrier. But now we have the problem of n, and to reject the noise, kg must be small. So if you put the barrier here, you would say, well, this is forbidden. And there is no solution because you are finding something that should be very big and very small at the same time. So what is the solution. Do you have any ideas? Now we have this other play, which is the frequency. What is the noise? I mean, if you look at the reference, what is the typical shape of a reference? You have time, and the reference is, say, something which is constant. Then you increase the temperature, the desired temperature a little bit. Okay? So it's something which is constant. And what about noise? Noise is something that varies widely. Okay? So probably they exist in different domains of frequency. I mean, if you are familiar at least with the Fourier series, decomposing a system signal into Fourier series. Okay. Now, a constant is not periodic, but suppose that you have something which is like this, like this, like this, square wave, slow. Now compare the harmonics of the reference with the harmonics of the noise. What is the difference in terms of frequency content?
Noise has high frequency.
Noise has much higher frequencies. Okay, so
So
noise appears in the high frequency. Disturbances are usually you step over the staircase and you stay there. I mean, you don't go stepping on the staircase, going out, going again, and going out, and then bring your children, and then going out and leaving your children and going to catch up. Okay, going out. That would give a high frequency signal. No, you just enter and you let go. So it's a small frequency content. So what is the trick here? Don't you have any idea based on this?
For small frequencies, the kg should be.
So use different kgs at different frequencies. What should we do? What is you have this barrier. This is the barrier for the reference. This is the barrier for the noise. I'm going to move this for different frequency contents. So which one am I going to move to the high frequency?
The small kg.
So the one that is related to noise. Okay, so I'm going to pick up this one, and I'm going to say that there is a frequency. Sorry, there is a frequency above which there is noise, and this should be below it. Okay, so my kg as a function of frequency should be something that should be above this one, probably like this, and should then decrease. Okay. Now, let's think about that story of the integrator. Now, I'm also having the horizontal frequency is also on a log scale. Okay, so omega is also on a log scale. I'm assuming that. So where is the zero frequency? Here. Onde é que está a frequência nula? Se está numa escala logarítmica. Isso é o vosso domínio, pá, químicos, pá. Escalas. Onde é que está o zero da escala logarítmica? horizontal. Where is the 0 of the horizontal scale if the scale is logarithmic?
Near to the line of 0, so
Here,
yeah,
what is the logarithm of 0?
1
Minus infinity.
minus
Logarithm of 1 is 0, but logarithm of 0 is minus infinity. So the 0, the omega equal to 0 is not here. You can't plot it.
okay.
You can't plot it. Okay, so you have this stuff. And this is a consequence of this analysis that we have. Now we are exploring the fact that we can put dynamic things. G is dynamic and K is dynamic, and probably this happens. So this is a different way of looking. Up to now, you had been looking at dynamic systems by means of the state model, which is essentially an analysis on time. Now I'm telling you about an analysis on frequency. Okay? Is this very strange? Yes, it is a little bit strange, but don't you have it manifestations on your day-to-day life? Tell me an example of a day-to-day life, something that you use every day, and in which you explore the fact that you have different frequency bands and you have activities on different frequency bands. Something that I'm sure you do every day. Think of television. You remember that we had analog television, and some years ago, they introduced TDT. What was the reason to have TDT? Apart from the fact that people had to buy a lot of new antennas and spend money and so on, this was good for a number of guys profit with that. But what was the technical reason for it? You remember?
No, I don't remember.
The government had sold the spectrum of frequencies. Okay. So when you have radio, you have different frequencies. You have one frequency to hear radio. I mean, when you hear Antena 1 or when you hear Radio Renascença, it's on different frequency bands. When you look at television, is again a much higher frequency band. You see? So this is, you are receiving all these signals in different frequency bands. It's the same as in here. Okay? Chemical people from chemical engineers never think they are not trained. It's a question of culture. You are not trained to think in terms of frequency. For electrical engineers, it's very natural to think about decomposing a signal into frequency components. Okay, we have the radio waves and so on. So it's quite natural. Okay, so you never thought, why is it possible to hear Radio Renascença without hearing at the same time Antena 1 or Antena 2 or TSF? Nunca tinham pensado nessa? It's because they come on different frequency bands. Okay. What happens is that when some guy speaks or when some music is played at Antena 1, what happens? Everybody speaks between, say, you are receiving signals up to 3 kilohertz. Perhaps not. I'm not really sure, but it's nothing more than that. 3 kilohertz over a telephone, 2 or 3 kilohertz. Okay. Now you pick up these signals between 2 0 and 3 kilohertz. And there are devices that shift these signals to a higher frequency band. Okay, there are methods for doing that, and you do that because you want not things to be mixed, because everybody speaks and makes sounds between, say, you can't hear more than 10 kilohertz, 20 kilohertz. People, for instance, myself, I can't hear more than 10 kilohertz. Sounds higher than 10 kilohertz. Okay, probably you can hear 15 kilohertz. Okay, so music, you have music between 0 and 15 kilohertz. Now you pick it up with a microphone, and you have an electrical signal between 0 and 15 kilohertz. Actually, it's not 0, it's 200 hertz. No, 0, you don't want it because it's an offset. Okay, and does not correspond to any sound. Now, what you do, you pick up this baseline signal, and then you shift to a frequency band. This is called a modulator. Okay, you have a modulator, and you have to negotiate which frequency band are you going to use. If you start emitting something, after 1 or 2 days, the police will come to your home and you will be arrested because you are doing something which is illegal. Okay, so you have to have a special permit to use each of the frequency bands. Now you have this modulator, which is an electronic device, and this shifts the signals. You can't hear it, but antennas work very well with high frequency signals, so they broadcast that. So you have a receiver, you have an antenna to receive it. Okay, and now you have a demodulator that again brings that to your baseline. Okay, that's how radio works, and many things. So what is the advantage of optical fiber over copper wires? Because in optical fibers, you can have a much wider bandwidth. Okay, the total bandwidth is much bigger than when you have a twisted pair of copper wires. Okay, and so you can put there more signals, you can put there more channels. Okay, TSF, antenna 1, antenna 2, so on and so on and so on. Now, in control, we also explore this difference. We don't have modulators or demodulators, but we have things. Let me now give you an example of how we can have a controller, which is not just a gain K that equally amplifies all the frequencies, but amplifies in a different way, different frequencies. It's an integrator. You remember? I said, if I put there an integrator, that's good, because the integrator, where am I? Oh, no, it's here. If I put here an integrator, then the integrator integrates this error, and when the error is 0, it stops integrating. So I have the correct value so that T is equal to R. Okay. So let's see what happens to an integrator. Any question up to now? So let's clean everything here. And so let's think about an integrator. This is an integrator. So you put here a signal. Now, let's think. It's a low frequency sinusoid. Okay. And the integrator it's up to some time gives you just the area. So it starts at 0. When you come here, you are at a maximum because you have integrated all this part. So up to that point, you had something like this. And then you are integrating a negative area, so it goes down. Okay, something like that. Actually, the frequency of the two waves are the same. Now, suppose that you have a much higher frequency signal here. Okay, what happens is that your amplitude will be much smaller. Well, this amplitude should be probably the same, the same as the other, but the frequency is much higher. Now, the integrator is based on this area, so it never has much time to go because it starts going down. So you have a smaller amplitude wave here. And if I put here even faster wave, imagine that this is a sinusoid very fast, okay? Then you will have something which is of the same frequency, but most important, the amplitude is much smaller, okay? So if you represent this as a plot in frequency, now you are used to represent operations or signals in time. Now we are going to think of signals in frequency content and the operators that change the frequency content of the system. So it amplifies some values, low frequencies here, but then it decreases. Actually, you can show that in log coordinates, this comes as a straight line. Okay, remember that this is a log coordinate, so the 0 of frequency is not here. If you have a 0 frequency, what is the amplitude at the output? Zero frequency is what? Is what type of signal?
Constant.
Is that constant? So if you integrate a constant, what you get?
A 0. No.
It goes
X.
up in steady state. What you get?
Infinity.
Infinity. So this comes from infinity. Okay, for omega equals 0, this is at infinity. You see? Now, if you place an integrator here, you are forcing the loop gain to go down. That's why the integrator is good, because it ensures high gain in the low frequency and rejects noise in the high frequency. Then this curve depends on K, which is the integrator, and G, which is the system. Okay? Now, This is the qualitative picture, but how can we make computations in an effective way? Any questions before we go on? So let's clean this stuff. So I want to describe a dynamic system by, I want to describe the dynamic system by an algebraic system. Suppose that I have this system. Suppose this is scalar, and I have y dot, or better to say, if I put here, let's put here x. And I say my system G is actually x dot equals to, let's say, A x plus BU. And I put a minus here, minus AX plus BU. Okay? Now, my trick is when I have x dot, I'm going to do a change and I associate to x, a big X. And when I have a derivative, I multiply by a variable s. This is a complex number. Okay? So my equation becomes xx equals to minus a x plus b u. So I solve it with respect to x, and this gives me x equal to, I don't ask you what is the result, because it would take about 2 hours to find the wrong answer. This should be b s plus a. You agree? I just solve it. Okay, this is an algebraic equation, so I solve it with respect to x. Now, x exists in the S-plane. So I have a real part, I have an imaginary part, and S is here. Okay, now I'm going to make S equal to j omega. So I say S is j omega, where j is square root of -1. That is to say, I'm here in this vertical axis. Okay, now this becomes what? Becomes x is equal to b j omega plus a u. Okay, now there is one thing which is wonderful. You say that the component, if you decompose this, suppose that you put here a sinusoid that you have. So you have your system. You have your system. It's this system. You can describe it by the differential equation in this way, or this is called the transfer function. Transfer function. It transforms the input to the output. So I have x, or capital X, and I have I have x at the output. So I have U, or capital U, and I have X, or capital X, and here I have one of those things. So I put here a sinusoid. Okay? And here I will have a sinusoid of the same frequency. But the amplitude is shifted. So if this is, say, sine of omega t, at the output I will have a gain. Let's call it capital A, sine of omega t plus some phase. Okay? And the gain, A, is the modulus of the transfer function for S equal to j omega. And the phase is the argument of B divided by j omega plus A. For omega equal to the frequency of the sinusoid. You see? So it's very easy to compute the transfer function. It's very easy to compute the transfer function. Now you do S equal to j omega, and you do these computations. Now there are graphic ways of looking at the computation. So let's see what does this system do, and then we go home. And next week we will continue to the frequency. Let me clear this. Fortunately, we need some space. So in this case, the gain, what is the gain? The gain is B. It's the modulus of B. Let's assume that A and B are positive, okay? So the modulus of B is B. Divided by, what is the modulus of j omega plus A?
Square roots of omega square plus A square.
So where are you? You have a real part, which is A, imaginary part, which is j omega. So this point is A plus j omega. And the length of this vector is the modulus, okay? And the length by the theorem of Pythagoras. What is the theorem of Pythagoras? I say this in Portuguese. Numa praia de Siracusa, diz Pitágoras a seus netos: o quadrado da hipotenusa é igual à soma dos quadrados dos catetos. There is a guy that I like very much, Gildo Ribeiro. You know Gildo Ribeiro? He has a professor of Greek culture, which is fantastic. So the RTP memory sometimes gives that. And this professor of Greek culture always tries to say the theorem of Pythagoras in different languages, Russian, Greek, and all sorts of funny, idiot things. I think he never tried in Portuguese. Okay, so the square root of this plus the square root of this is the square root of the hypotenuse. Okay, so which is the length? So it's omega squared plus a squared square root. It's okay. You know theorem of Pythagoras, Jose and Café. You don't know. It's
Yes, of course I know. Like really.
You are in a place. Someone wrote that everything is based on the theorem of Pythagoras.
Really? Okay.
Yes. So apart from the guys of non-Riemann non-Euclidean geometries, okay, that's the department of mathematics. Everything else is based on the theorem of Pythagoras. So, Kaveh, you should. How is it possible to? What is your basic course in Iran? Electrical engineering? No, mechanical engineering.
No, metallurgy engineering.
Material.
Yes.
But you never studied the
Pythagoras. No.
We studied Pythagoras when we are really small, or like 7th grade.
But
Because that's when we start to
this
give
is something
geometry.
that you are always using. So if you have a rectangular
okay.
triangle, you have
yeah.
A, you have B. How do you call this? And you
okay,
and
yeah,
C squared is A squared
yes, A
plus
squared
B
plus
squared.
B squared. Yeah, this is the name. It is there.
What is that? What do you call it?
No, it's a Pythagoras.
Oh, spell it.
Pythagoras.
Pythagoras. Oh,
Yeah,
I'm sorry, my Greek is not as good as yours. I agree with that.
Because is it the Pythagoras? I was like, this name I've never heard. But yeah, this is
Lost,
Okay, but you know the result.
translation.
But
So-
Jose was right. We've learned that in the 8th grade, 8th or 7th
Yes,
grade.
probably.
We learned. Yeah. So this was in
see,
the
that's
school.
When you were about 12 years old, probably.
Yeah,
Yeah.
12, 13 years exactly.
That's why math is perfect, because it's beyond languages.
That's
Doesn't
right.
matter which,
Yeah,
You like
doesn't
the
matter which
formula.
language you
But
speak,
yeah, when you-
it is the same.
So you have, this is the modulus. Okay. So don't forget what was the original problem. You have excited your system with a sinusoid. Then you had a sinusoid at the output. Well, this only happens after a while. There is a transient, and then you have a sinusoid of the same frequency, but with a different phase, which is the argument of the transfer function for s equal to j omega, and with an amplitude, which is the modulus of the transfer function for s equal to j omega, which is this. Okay. Now, what happens? At low frequency, what is the gain? So at frequency 0, what is the gain? If you make omega equal to 0, you get what?
B divided by A.
B divided by A. Is that something that we should expect or not? Look at the differential equation. If U is a constant, in steady state, what is x dot? In equilibrium, what is x dot? U is a constant, and there is a transient, and then x approaches an equilibrium, and in equilibrium x is constant, so x dot is what?
0.
0. So and the constant, and x is what? If x dot is 0, x is what?
Constant.
And what is the constant? So we have 0 equals to minus a x the equilibrium plus bu. So x bar is what?
B divided by A times U.
And what is the static gain?
B divided by A.
By A. So it agrees, at least in this case. Okay. Now, what happens to omega when omega grows? What happens to the gain? What happens to the gain?
Decreases.
It decreases. It decreases. Okay. So this is a low pass system. You only have gain if you do a plot. If you do a plot in which you have the gain of the system, let's call it G, okay? It starts, and this is omega, now in linear coordinates. It starts in B divided by A, and then does something like this. And approaches 0, okay? So there is a frequency band for which you can excite your system. If you excite your system at high frequencies, you get nothing because the system does not respond enough, no? You know that you have your car. Now, try to accelerate it slowly and then decrease the velocity slowly. It responds. The velocity increases and then decreases. Now, try to increase it a little bit. And there is a point in which you are pressing your pedals too fast and the car does not respond. Okay? Or if I tell Jose, stand up, and he stands up, then sit down, and he sits down. Now, if I start saying, stand up, sit down, stand up, sit down, he's caught in the middle of the way. Okay? So it's a low pass system, you see? Things have systems have bandwidths, usually. And their response depends not only, it's not constant with frequency, it depends on frequency.
Which means also the time as you give the example, so it must be like in a sequence of the low frequency. It is like it shouldn't be too fast, so it must be in order. So
I'm not sure if I understand you.
No, I mean, would you repeat again this?
If I give an order which is too fast, your input is too fast.
Okay.
You don't have enough gain. So this means that the system has not physically, you will not able to respond to follow your orders. It will be caught in the middle. Vai ser apanhado no meio, fica ali acertado. Okay.
Okay, now I got it.
Let's see what happens to the integrator now. Let's look at the integrator. So, an integrator I want to describe just a few minutes more. So I have U and X, and X of T is the integral from 0 to T of U sigma d sigma. Now, I don't have any theory for the integral. Actually, I can't have it But for the moment, we don't have. We only know how to tackle derivatives. How can I replace this? How can I get a differential equation for x? Suppose that I differentiate everything here. So dx dt is equal to what? Is the derivative of the integral of u. So
It's u.
it's u. So dx dt equals to u describes an integrator. It's an equivalent form of describing the integrator. Now, in terms of this algebraic method, how can I write an equation for capital S x? So what is the effect of the derivative? You remember what we were doing?
Sx.
Sorry?
S times x.
S times x equals to u. So x is equal to, in terms of u, this is very difficult. You agree? Just use it algebraically. Now, once you have done this step, then things become algebra, pure algebra. Okay? Now, I want to see the effect in frequency. So I do S equal to J omega, and I want to see what is the gain over frequency. We know that it decreases, but it was based on some heuristic arguments. So I replace S by J omega. So the gain, let's call it A, was 1 divided by J omega modulus. And this is what? This is what? What is, if omega is a real number, that's the frequency. Modulus of J omega is what? 1 divided by modulus of J omega is?
1 divided by omega.
1 divided by omega. Okay? In this case, if we have the C-plane, where is J omega? J omega is here. So the modulus is just a segment, which is omega. This is J omega, and the modulus is just omega. Okay? So if you do a plot in linear coordinates, for 0, you get something which is infinity. For 0, you get infinity, and then it decreases. Okay? Now, if you take the logarithm to see this in logarithm coordinates, if you take the logarithm of 1 divided by omega is what? In terms of omega?
Minus logarithm of omega.
Minus logarithm of omega. So if I want to do the plot in logarithmic coordinates, now I have log of omega. I have something for what is this value of frequency? Omega is equal to
1.
1. Okay, and you have this straight line. Now, the electrical engineers use the so-called dB, which is 20 logarithm of something. Okay. And this comes, you can see that this comes at a rate at 20 logarithms per decade. That is to say, when you move 10 in a factor of 10 in the omega, you have moved 1 unit in the logarithm, and you have fall down 20 logarithms, 20 dBs. Okay, it's just a matter of convention to express things in dBs. And you see that the fact that you use logarithm coordinates transforms these curves in straight lines, which is quite useful. There is actually a technique that allows you to do these plottings. Okay, so let's stop here, unless you have any question.
No.
So today we learn important things. One was that final part of the last lecture, in which we saw that specifications for your loop gain, and these specifications to be feasible, they must depend on frequency. And now we started this stuff of relating dynamic systems, so starting with linear equations, from linear differential equations to these so-called transfer functions, so that you can do computations in the frequency domain in a fine way, in the simplest way. Okay, we are going to explore this a little bit to see how can we design the controllers and study stability in a systematic way and so on. And the advantage is that now, when you do this step from a differential equation to this S domain, actually this is the Laplace transform. When you do this move, everything becomes algebraic. You forget about the properties of differential equations. You are only concerned with algebraic manipulations. Okay, so that's it for today, and study a lot. Till next week.
Thank you.
So see you next week.
Thank you.
Bye.
Bye-bye.
Bye.
Bye-bye.
Bye.